Good afternoon, students. So my name is Siddharth and I am a new chemistry teacher. So in this lecture we'll be discussing about the hydrogen atom. Previously your ma'am has discussed about Schodinger equation and one-dimensional box, so I'll be continuing with the remaining topics. Okay, so you see the hydrogen atom, it is a one electron system. Say we have hydrogen, it is its electronic configuration is 1s1, means we have the nucleus and surrounding the nucleus we have only one electron which is revolving around the nucleus. Okay, so the Schodinger equation is completely solvable for this hydrogen atom. Okay, means we can solve the Schodinger equation for one electron systems. Say for example, if we take helium, its electronic configuration is 1s2. Okay, and lithium, its electronic configuration is 1s2, 2s1. Okay, now see say for helium, if we remove one electron, say it will become helium plus ion. Okay, so for helium plus ion, the electronic configuration will be 1s1. okay, and for lithium, if we remove two electrons from lithium, we will have Li2 plus ion. So for this one also the configuration will be 1s1. okay, now see this helium plus ion and lithium 2 plus ions, they have the same electronic configuration as that of hydrogen. Okay, so this type of systems, say this type of ions, or say hydrogen atom, or say this type of ions, say helium plus and lithium 2 plus, so this type of ions, these have only one electron in it. Okay, so this type of electron this type of systems are called one electron systems. Okay, and the Schodinger equation is solvable only for one electron systems. Okay, so you have got this expression for the Schodinger equation. It is h cross square by twice m del square psi plus v psi equal to e psi. Okay, now here you might get confused because you see h cross, it is nothing but h by 2 pi. Okay, so h cross square will be h square by 4 pi square. Okay, you just replace this thing in this one, so you will be getting minus of 8 pi square, oh sorry, this thing, you will be getting minus of h square by 8 pi square m del square psi plus v psi is equals to e psi. Okay, and this thing, this part, this this can also be written as h psi is equal to e psi. Okay, where h is nothing but your Hamiltonian operator. Okay, and this Hamiltonian operator, it is this thing, h square by 8 pi square m del square plus of v. This part is your Hamiltonian operator. Okay, now this is the Schodinger equation. I think your ma'am has already discussed this, so I will not go into it. So this is the Schodinger equation, and this equation, using this equation we can find all the informations regarding a hydrogen atom or single electron systems. Okay, so you see this Schodinger equation, this thing, this del square, na? You got this thing as del square. Del square means nothing but del square is your Laplacian operator. Okay, and del square is written as del square d square by x square, d square by y square plus d square by z square. Okay, this is in 3 dimension. Okay, in 1 dimensional, the Schodinger equation is simply like this: minus of h square by 8 pi square m d psi by dx plus v psi is equal to e psi. Okay, so this is the Schodinger equation in 1 dimension. Okay, so this is the Schrödinger equation in one dimension, and this where we use the Laplacian operator, it is in 3 dimensions. Okay, and m is nothing but mass of the electron, and v is your potential energy of the electron, and E is the total energy. Okay, so this is the basic thing about the Schrödinger equation. So we'll be solving this equation for for the hydrogen atom. Okay, now see, the thing is that this Schrödinger equation that we have discussed, that we have studied, this thing is in Cartesian coordinates. Okay, this Schrödinger equation is in Cartesian coordinates, means it is in x, y and z. Cartesian coordinate, I think all of you know what is Cartesian coordinate. Say we have this 3 axis system, na Cartesian coordinate system. We have x axis, we have y axis, and we have z axis. Okay, now you see this, if we just draw a cube, just give me a minute. Say this is a cube. Okay, now if we take this point, okay, this point, it is equidistant from the x axis, y axis and z axis. Okay, this point is equidistant from x, y and z axis. So this point, it will have the coordinate, let's name this point as P. Okay, and P will have coordinates x, y and z. Okay, now this P, if we join, means say if we draw a line from the origin to P, okay, so this line is nothing but your radius. This line, this thing, this is nothing but your radius. Okay, and say let me draw it nicely once, it will help you to understand well. Say we have this one, this is the axis system, and this is the cube. Like this. Okay, and this thing, this is the point P, and it has the coordinates x, y and z. Okay, so this is your z axis, this is your y axis, this is your x axis, and we have drawn a line from this origin, from origin to the point P. Say let me do it with different colors, say this one. Okay, so this one. Okay, so this line is nothing but your radius. Sorry, this is not x, this is r. Okay, this will be r. So this is called your radius. Okay, now see what will happen. Say we have two more things. We will say we are converting the Cartesian coordinates, say x, y and z. We will have to convert this into spherical polar coordinates. Okay, means the Cartesian coordinates are x, y and z, and spherical polar coordinates are r, theta and phi. So we have to convert this Cartesian coordinates into spherical polar coordinates, then only the Schrödinger equation will be easily solvable, because in Cartesian coordinate systems the variables cannot be separated, so the Schrödinger equation cannot be solvable. Okay, so to solve the Schrödinger equation, we have to convert the Cartesian coordinates into spherical polar coordinates. Okay, so this polar coordinates are r, theta and phi. So this is r. Now see, we have an angle here with the z axis and this radius. Okay, this angle is your theta. say this angle is theta, this one is theta, okay. And what we can do, we can draw a projection of this radius, okay, in this one, say like this. So in the xy plane, so this is your xy plane, this is your xy plane, okay. So in the xy plane, what we have done, we have drawn a projection of this r, means the radius, we have drawn a projection of this radius in the xy plane, and then one more angle will be formed between this one, the x-axis, and this projection, okay. Now the projection of r in the xy plane is this one, the purple line, and the angle between this x-axis and this purple line, means the projection, is termed as phi, okay. So this angle is nothing but your azimuthal angle. This angle is called your azimuthal angle, and the theta, that is called your zenith angle, okay. So using this say graph or diagram, we can convert the Cartesian coordinate system into polar coordinates, okay. So after converting, you see these are the relations that we get. So z will be r cos theta, y will be r sin theta sin phi, and x will be r sin theta cos phi, okay. So these are the relations that we get from the means that we get between the Cartesian coordinate system and the polar coordinate system, okay. So after converting, you see the Laplacian operator, it takes this form. The Laplacian operator, it takes this form. Del square is equals to 1 by r square d by dr, r square d by dr, plus 1 by r square sin theta d by d theta, sin theta d by d theta, plus 1 by r square sin square phi d square by d square d phi square, okay. So this is the Laplacian. See this I will not go into the mathematical part because it is very lengthy, say 6 or 7 pages it will take. So and it is not in your, means it is beyond the scope of your syllabus, okay. So you just have to memorize this Laplacian operator, means you have to, means in the exams they will not ask you to derive this thing, say derive the whole Schrödinger equation, say for hydrogen atom. They will simply ask you the applications, means how to use it. In chemistry, what we do, we don't do the mathematical part, we use it, everything, all the laws, formulas, whatever we do, most probably we focus on the applications of those things, okay. So what we do, you just memorize this Laplacian. It's just, if you write it 2-3 times, I think you will memorize it. So this is the Laplacian operator del square, and it takes the form in this polar coordinates, okay. It takes this form in the polar coordinates. So you see this Laplacian operator, if we use this one in the Schrödinger equation, then the Schrödinger equation takes this form, this one, then the Schrödinger equation takes this form. Just in place of del square, we have to put this spherical polar coordinates term, and we will get the Schrödinger equation in spherical polar coordinates. This is the Schrödinger equation in polar coordinates, okay. Now this Schrödinger equation is easily solvable, and the solution of this equation will be of the form this one. See, we had 3 parts now. One is means in the polar coordinates we have a radial part, r, means a function of r radius, and we have 2 more parts. Say one is a function of theta, this one will be a function of theta, and one will be a function of phi, okay. So this thing, say this part r, the function, this part which is a function of r, is called your radial function, or we can say it as a radial part. The solution of the Schrödinger equation is divided into 2 parts, radial part and angular part, and this part is called your angular part or angular wave function. angular part or angular wave function. Okay, so this is the solution of the Schodinger equation. Say we can write this one in this form also, as a function of r and as a y as a function of theta and phi. Okay, now here you get two more terms, n, l and l and ml. Okay, these three more terms you will get to know as n, l and ml. So what are these actually? You see, n, it is your principal quantum number, L is your azimuthal quantum number, or you can say orbital angular momentum quantum number also. Okay, ml is your magnetic quantum number, and ms is your spin quantum number. Okay, these are the four quantum numbers that we use to explain the structure of an atom. Okay, these are very, very important. So let me discuss this thing in a brief. We just see, just once, give me a minute. You see, first what we have the nucleus, where all the protons are present. Surrounding the nucleus we have shells like this. Let me do it with different colors. Okay, say this is your first shell, this is your second shell, and say this is your third shell. Okay, so this is first shell, second shell and third shell. Now this n means the principal quantum number. It tells us about the shell. Okay, means which shell the electron is present, or which shell we are studying. So this one, for this first shell, the n value will be equals to 1. For the second shell, the n value will be equals to 2, and for the third shell, the n value will be equals to 3. Okay, means the principal quantum number gives us knowledge about the shell. Then comes the azimuthal quantum number. It tells us about the subshell. Okay, it tells us about the subshell. Now n can have values 1, 2, 3, 4 like that. Okay, up to n, and L will have values from 0 up to n minus 1. Say if value of n is 2, then L will have values 0 and 1, means L will have two values. Okay, so n is 2, then L will have two values, 0 and 1. Say n is 3, then L will have three values, 0, 1 and 2, like this. Okay, so and one more thing, this thing, say this L values na, say L is equals to, L can have values of 0, 1, 2, 3 up to n minus 1. Okay, it will be 1 less than n. So you see one thing, this 0 means nothing but your S, 1 means P, 2 means D, and 3 means F. Okay, these S, P, D and F, these are your subshells. Previously you see in college, or means in your class 11, 12, I think you have studied this one as S orbitals, P orbitals, D orbitals, F orbitals, but actually these are not orbitals, these are subshells that are present inside the shell. Say for n equal to 1, we have only one, say like this, we have only one subshell, so it is called 1s. Okay, this one is called your 1s. For n equal to 2, we have two subshells, one is your S and one is your P. Okay, for you see, for this one is 2s, this one is 2p. Okay, these are subshells, 2s and 2p subshells. Similarly for 3, you will have 3, I think third shell will have 3s, 3p, and we'll have 3d also, like this. So this is 3d, this is 3p, and this is 3s. Okay, so the principal quantum number n, it tells us about the shell, means in which shell the electron is present, or what we are discussing about. In this one, say the azimuthal quantum number or orbital angular momentum quantum number it tells us about the subshell. Okay, means subshell means L, if L is 0, then subshell is S, if L is 1, subshell is P, if L is 2, the subshell is D, and if L is 3, the subshell is F, and beyond that it is not required. Now see the next quantum number, it is the magnetic quantum number. Okay, the magnetic quantum number ml, it tells us about the orbital. The magnetic quantum number, it tells us about the orbital, means in which orbital the electron is present. Okay, so ml, you see for ml what will have, it will have values minus L to plus L. Say if L is equals to 2, okay, then ml values will be minus 2, minus 1, 0, plus 1, and plus 2. Okay, say if ml say if L value is 3, say if we have L value as 3, then ml will be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay, now see for this is for L equals to 2, this is for L equals to 3. Okay, now L equals to 2, you see L2 means d orbital. Okay, so discuss this one. L2 means d orbital. So d orbitals, we all know it is like this, 1 2 3, sorry, a d subshell, it is 5 orbitals, 1 2 3 4 5. So this one is minus 2, minus 1, this is 0, this is plus 1, this is plus 2. Okay, these are the 5 d orbit, 5 orbitals that are present in the d subshell. Similarly, if you take L equals to 3, if L is 3, then we have the F subshell. So for F we have 7 orbitals, 3 4 5 6 7. Okay, 7. So it will be like this, minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Okay, so these are the 7 orbitals that are present in the F subshell. Okay, so and we have one more, the last quantum number ms, it tells us about the spin of the electron. The spin of the electron means the electron can be present either like this, means in the upward spin, or it can be present as downward spin. Okay, so if it is upward spin, it will be plus half, if it is downward spin, it will be minus half. Okay, now see how this you can also relate with the shoe. Okay, say if you buy a new pair of shoe, say in the box you have a shoe, so you see the shoe will be, one shoe will be like this, and other shoe will be like this, like this. Okay, means in the means the pair of shoe, they are present opposite, means one is upside and one is downside. Okay, so the electrons are exactly present in the exactly same way in an orbital. Say one electron, say if say if this is a orbital, then one electron will be present like this in the upward spin, and if another electron comes, then it will be present as downward spin. Okay, like this, one will be in upward spin, one will be in downward spin. So you can correlate this one with the example of shoes, means if new pair of shoes when you buy, how it is placed in a box, you can relate with that one. So the upward spin, it will have spin quantum number as plus half, and downward spin will have minus half. Okay, so using this 4 quantum numbers, we can exactly explain the structure of atom. Okay, previously many different models have been suggested. Say we have Thomson's model, then Rutherford's theory, all those things, Bohr's model. Okay, I think your ma'am has discussed all those things, but all those things fail to explain the structure of an atom completely. Okay, and this quantum mechanical model means using this four quantum numbers, we can exactly explain the structure of an atom. Okay, first thing you remember the principal quantum number n, it will give you knowledge about the shell. Okay, secondly the orbital angular momentum or azimuthal quantum number, it will tell us about the subshell. Then magnetic quantum number will tell us about the orbital, and then the last thing, the spin, means the how the electron is placed in the orbital, that will be uh, uh, given by the spin quantum number. Okay, now this is the basic thing about the spin and magnetic quantum numbers, and means all the four quantum numbers. Okay, so now you see we have from the solution of the Schodinger equation for hydrogen atom, we we got that it has two parts. One is the radial part, one is the angular part. Okay, so let us discuss about the radial part first. Okay, now you see the radial part means r, it does not have any physical meaning. Why? Because you see we have drawn the graph like this, means the Cartesian polar coordinates, it was like this. Okay, and this was the radius, this is the point P. Now see, in this radius, say if we consider this origin as the nucleus, then in this radius the probability of finding the electron will be very low. Okay, means almost negligible, because it is just a line. Okay, and electron we know that is always in random motion, means the electron always keeps moving. Okay, so as the electron always keeps moving, so it will not be fixed in one position. Okay, so and this radius, it is just a simple line, so in this line the probability of finding the electron will be very, very less. Okay, it's almost negligible. So that's why this radial function, it does not have any physical significance. Okay, but if we take r square, means if we square the radius, it will give us the probability of finding the electron. Okay, in a small volume, say dV. Okay, and the volume will be given as, say dV will be equal to r dr, say r square dr sine theta d theta d phi. So this is the volume element. Okay, this is the expression for volume. dV will be given as r square dr sine theta d theta d phi. Okay, this is the volume element in polar coordinates. Okay, and r square will give you the probability. Okay, and this term, that 4 pi r square, small r square, capital R square, this is nothing but is known as your radial distribution function. And this tells us, this radial distribution function, it gives us all the information about the probability of the electron, means where the electron can be present in a subshell or in a orbital. Okay, so we have some plots. These plots are very important for this radial function. Say for 1s, the graph is like this. Say we have plotted this r with r by a, small r by a. Okay, so this is just you can see it is an exponential graph. Say if this is the nucleus, say if we say this is the nucleus, so on going far from the nucleus, the probability of finding the electron decreases, and it is obvious. You see, say this is s orbital and this is the nucleus. Okay, now one electron is present and one proton is present inside the nucleus. Okay, now the proton that is present in the nucleus, what it will do, it will pull the electron towards itself. So you see the probability of finding the electron will be higher nearer the nucleus. Okay, because there is a force of attraction. We all know that in physics now, opposite charges attract. So there will be probability of finding the electron, means say higher probability of finding the electron just nearby nucleus. And if you go far away from the nucleus, as you go far from the nucleus, this probability decreases. Okay, that's why this graph, it is exponentially decreasing like this. Okay, and it comes up to 0 at some point. Okay, Now see, for the second one, this one, for 2s, first the probability it will decrease, okay, then again it will increase, okay. Why? Because in the second shell the number, say in the first shell this is like this, in the second shell what will happen, if we add the second shell, means more electrons. Say here we will have 2 electrons like this. First we fill up the electrons like this, now say we have say we have lithium, okay. Lithium is like this, 1s2, 2s1, okay. First we filled up electrons, this first shell, 1s shell, and then we'll fill up electrons in the 2s, okay. So here in the 1s, when 2 electrons are fully filled, then the next electron will come here, 3 electrons. So similarly what happens, this attractive force between the nucleus and the electron is balanced by this repulsive force between the 2 electrons in the 2 different shells, okay. So that's why what happens, first it decreases and then again it increases, okay. For 2p it is like this, it will be increasing first and then it will be decreasing. For 3s, same thing, first it will decrease, then again it will increase, and then again it will decrease, okay. Then for 3p it is like this, first it will be increasing like this, just in the 2p now, 2p it increased and then decreased, and 3p will be, first it will be increased, then it will be decreased, and then again it will be increasing. And 3d it will be like this, first it will increase and then decrease. Now see, as you go from the s orbital, say say if you compare the s 1s, 2p and 3d, okay. Say s, p and d orbitals, if you compare, you see this peak, okay, means this thing it decreases, okay, means the altitude, say it's decreasing, okay, because the s orbitals, say 1s, it is the closest to the nucleus, okay. That's why the force of attraction will be higher. P is little bit outside, so it is less, and d it is little bit more outer, so that is more less, means the probability of finding the electrons it decreases as we go far from the nucleus, okay. Now one more thing you can find out from this graph, say these are the graphs for radial function. So radial function does not have much significance. Much significance is that you can find out nodes, okay. Nodes, how you will find out, I think your ma'am has discussed the formulas for finding nodes, we will also discuss. I'll just tell you roughly. We see these are the points now where this curve it becomes 0, means it touches 0. So these points are called your nodes, okay. Nodes are nothing but those regions, okay, all those locations where the probability of finding the electron is 0, okay. Now how we can calculate means the nodes, number of nodes from this graphs and all, we'll discuss in this lecture only, just in the later part, okay. So let us first discuss about the radial plots for the radial distribution function, okay. Now see, the radial distribution function, you see, when we discuss this plots now, say the radial functions, it had positive values, say this part is positive, it had negative values also, minus the bottom part, and it had 0 also, okay. Means this r, it can have values of plus, it can have values of minus, it can have values of 0, okay. Means minus negative values are also possible, positive and 0 is also possible, okay. But when we take probability, means radial distribution, see the radial functions, why it is not significant, that also we can say that the probability of finding the electron in an orbital, we all know that probability can have values of 0 or 1, means probability it can be either we don't have any probability of finding the electrons, or we have probability of finding the electrons, okay. So in maths, I think you have studied that probability can have values only 0 and 1, it cannot be negative, okay. But in radial functions, you see the graph, it goes, means in the minus y axis, okay. So it has negative values. So since it has negative values, so it cannot tell us about the probability of finding the electron, okay, because exact location we cannot find out for the electrons, because it is a microparticle and it is continuously moving, okay. but we can just tell that the electron is present in this region, means we can give the probability that the electron might be present in this means in a particular volume or in a particular say area. Okay, so you see the radial distribution function, it tells us about the probability because we take r square. Okay, so r square means tells us about the probability of finding the electron. That's why this is more significant, because you see it does not have values of negative values. Okay, always remember that if you have plots for radial function, it will have negative values. Okay, but radial distribution function will never be negative. Okay, just like the wave function. Now wave function does not have any significance. Okay, but if you take the mod psi square, okay, it gives us the probability of finding the electron, so it has significance. Okay, and this can never be negative, this cannot be negative. Okay, this cannot be negative. Now for if we put, this will be like this. Okay, 4 pi square will be there. Yeah, that's pi square, 4 pi r square, small r square, capital R square. Okay, so this probability, it will be like this. Say for 1s, you see the highest probability, because 1s orbital is, this is for 1s, this is 2s, this is 2p, this is 3s, this is 3p, and this is 3d. Okay, so for 1s the probability is the highest. Okay, because it is just an means closest to the nucleus. Okay, that's why the probability of finding the electron is maximum in the 1s orbital. Then in 2s it will be little bit less compared to 1s, and 3s will be less. Now see, here you have 3 peaks. Okay, in 1s we have only 1 peak. Okay, that is the maximum. In 2s we have 2 peaks. Okay, and 3s we have 3 peaks, like this. Okay, now see, as you see this first and the second peaks are smaller, and third peak is little bit say larger. Okay, or higher. This is because this the same thing, the distance. Say 1s, it is the closest to the nucleus, so probability to find the electron is high, because higher near the nucleus, because attraction means electron nuclear pull will be higher. Okay, similarly for 2s and this 3s, the attractive forces or the nuclear pull will be little bit lesser. Okay, so that's why the peak its altitude, it decreases. Okay, so for 2p it will be like this. For 3p similarly we have 2 peaks. Say 1s has 1, 2s 2, and 3s 3. Similarly for 2p we will have 1 and say 3p it will be 2 peaks. Okay, now see these peaks, it's not steep. Okay, it's broad peaks, means the altitude, it decreases. And when we'll be discussing about the angular function now, then I will be telling you about why these peaks are like this. Okay, why these are not steep, means why just like the 1s now, why these are little bit broad peaks, not steep peaks. Just for the time being, what you do, you just have to memorize these graphs, because these graphs will be asked in the examinations. Say 1s, what are the plots for radial distribution function for 1s, 2s, 3s, or 2p, 3p, and 3d. Okay, these are the 6 plots that will be important for you. And for the radial functions also, we just memorize the graphs, because these graphs are very important. Okay, this means, yeah. Okay, so now let us so this is the just the this one, this is all about the radial part. Okay, now we will be discussing about the angular part. So you see, the angular part means we had this one, this was our graph. Okay, so this graph, we had a point like this. This is P had x, y, and z coordinates. This angle was theta, and for this P we had a projection like this, and this angle was phi. Okay, now this theta and phi, this constitutes of the angular part. Okay, so this will tell us about the surface boundaries, okay, of an electron. Just like in physics we have na, say we have a charge, say any charge, say we have a positive charge. Okay, so this positive charge will have some field. Okay, why field means electric field. You have studied field means what? Say the region in space where the where we experience say attractive or repulsive forces relative to the charge. Means in if we place any particle, say if we place a negative particle in this inside this electric field, then it will have it will be this one, it will experience a force of attraction. Say if we place put negative, then it will be a force of attraction. If we place a positive, it will be a force of repulsion from this charge. Okay, so if we place these particles outside this electric field, there will be no force of attraction or repulsion. Okay, so that region up to which the, say we can say that region in space up to which the attractive or repulsive forces of the charge is experienced is called electric field. Okay, similarly what we can do, you see the nucleus will have a positive charge. Okay, so there will be a certain boundary up to which the force of the nucleus will be valid. Okay, means if an electron is present, means up to which the nucleus will pull the electrons, there will be a certain boundary, and outside that boundary the force of the nucleus will be invalid. Okay, means there will be no force of the nucleus. Okay, outside that region. So that region means the boundary region up to which the force of the nucleus is acting or it's valid is called is given by the angular wave function. Okay, and those boundaries means are called boundary surface areas. Okay, means you see this diagrams these are called your polar diagrams. Okay, so for 1s it is like this, because 1 is it is spherically symmetrical, so it will be surrounding the nucleus from all sides. 2s it will be little bit larger compared to 1s. Okay, because the shell is increasing. Say if 1s is like this, 2s will be little bit larger than 1s. Okay, so 1s is simple because it's spherically symmetrical and it will have positive part. Okay, and plus minus is nothing but it tells us about the symmetry. Okay, because symmetry, why it is important, because you see for the orbital overlap now, when we'll be discussing in the next lecture, we'll be discussing on molecular orbital theories. That time I'll be discussing about the overlaps, means how two atomic orbitals they overlap to form a molecular orbital. Means say two atoms they combine to form a molecule. Okay, so what happens when the two atoms combine, they form a bond. Okay, so that bond na, how that bond is formed. Okay, for the formation of the bond, what we do, we need the orbitals to overlap. Okay, and in that overlap the symmetry of the orbitals should match. If the symmetry of the orbitals match, then only we will get bonding orbitals. Okay, then only the bond will be formed. So for the symmetry is important. Now see the p orbitals, we need know that in the p subshell there are three orbitals. Okay, 2px three subshells, px, py and pz. Okay, px, py and pz. Px means the lobes of the orbitals will be in the x-axis, means it will be like this. Px will be like this, the lobes of orbitals will be in the x-axis. Py, the lobes of the orbitals will be in the y-axis, and pz, the lobes of the orbitals will be in the z-axis. Okay, means lobes means the probability of finding electrons will be higher in these positions. Okay, say this center of the two lobes is the nucleus, and the probability of finding an electron in the nucleus is 0. Okay, so this is px, py and pz, and you see one part is positive, one is negative. Okay, the positive part, it is the positive symmetry, and negative is the negative symmetry. Now see it's symmetry. I just tell you briefly one thing. Say you have p orbital like this, and another p orbital is like this. Okay, say this one. Now you see this is also plus, this is minus, this is plus, this is minus. Now this plus, this is positive symmetry, this is also positive symmetry, so they will overlap. and when they will overlap, they will form like this, they will form like this. Okay, so this is called the formation of a bond. Say this is an atom A, this is atom B, so there will be a bond formed between A and B like this. Okay, so that's why symmetry is important. Say if this is positive, and say if we say this one, say this is positive like this, and this is opposite, negative, then this will not overlap, this overlap will not be possible. Okay, means this overlap, if the symmetry is same, then the overlap will result in low energy orbitals that are called bonding orbitals. And if the overlap is means like this, if the symmetry does not match, then energy will be increased. So those things we'll be discussing in molecular orbital theory, okay, in the next lecture. Now see, from the angular part tells us about this boundary conditions. So this shape of the orbitals now, it comes up from the angular wave function. Okay, now these are the 6 d orbitals you see. So the d subshell, it has 6 orbitals, sorry, the d subshell has 5 orbitals. Okay, now dxy, dyz and dzx. Okay, these are the planar, these 3 are the planar d orbitals, x, y, y, z planes. You see this the lobe, why it is planar, because you see the lobe of the orbitals now, these are present in planes. Okay, this is the xy plane, yeah, this is y. Okay, this is the yz plane, so this is dyz, here it is xz, so this is dxz, and here is xy, so this is dxy. Okay, then we have axial, these are the axial d orbitals, the 2 axial d orbitals. Here you see the lobe of the orbitals, dz square, no? It is present along the z axis, this is z. Okay, and here this is the lobes are present in the x axis and y axis, so it is called dx square minus y square, and this is dz square. So these are the 5 d orbitals that are will be using in further classes. Okay, so you just memorize these things, and the concept is also important, is how we get, is what we have, say, let us summarize the things. We have discussed about the hydrogen atom, the Schodinger equation, the form that we got. Okay, then what we have done, the Schodinger equation, we have to convert it into means the one that we have studied, it is in Cartesian coordinates, say x, y and z. So we have to convert the Schodinger equation that is present in Cartesian coordinates to polar coordinates. Okay, so in polar coordinates we have to convert it into r, theta and phi. Okay, so after converting, what we will do, we will solve the Schodinger equation. So after solving the Schodinger equation, we got a solution which has 2 parts, one is the radial part, one is the angular part. Okay, so the radial part means the radial function does not have any physical significance. Okay, but the probability of that radial function is the radial distribution function r square, that has physical significance, because it tells us about the this thing, probability of finding the electrons in the orbitals. Okay, so for that we got 2 for radial functions also we have discussed some plots, and for radial distribution functions also we have discussed some plots. Okay, and the radial function plots can have negative value, positive value or 0, but for radial distribution function we can have 0 or positive value, negative value is not possible. Okay, then it comes to the angular part, means the angular wave function. Angular wave function, it tells us about the shape of the orbitals. Okay, means the boundary surface regions of the orbitals. Okay, so in that one we got s orbital, p and d. So in s subshell we have only one orbital, so that is s orbital. In the p subshell we have 3 orbitals, px, py and pz, which is their lobes in the along the respective axis. Okay, and in the d subshell we have 5 orbitals, 3 are planar, dxy, dyz and dz square, and 2 are axial, dx square minus y square and dz square. Okay, the last thing that we'll be discussing in this lecture is your nodes and nodal planes. Okay, now you see, nodes or nodal planes are those regions where the probability of finding the electron is 0. Okay, so you see the radial nodes are given by this formula, n minus of L minus of 1. N is principal quantum number, L is your orbital angular momentum or azimuthal quantum number, and formula is n minus L minus 1. Angular nodes is given by L, total nodes is given by n minus 1, and total number of peaks is given by n minus of L. Okay, So nodal planes and nodes, how I will discuss, you see. Say we have this one. Say let us take this axis. So, yeah, this is a p orbital. Okay, so yeah, this is x axis, this is y axis, this is z axis. So this one is nothing but your pz. Okay, pz orbital. Now see, this is a node. Okay, this is a node because probability of finding the electron here is 0. Now if we draw a plane through this node like this, means you just imagine that this is vertical, axis z axis vertical, means in the plane of this paper, and we have a plane that is present vertically like this. Say we have like this, means just give me a minute. Say this is the plane, this is the plane. Okay, and we have the orbital like this, like this. Okay, so this is the node. Okay, this is called your node, and the plane that is passing through the node is called your nodal plane. Okay, and the probability of finding the electron in the nodal plane or the node is 0. Okay, and that we can easily find out from the quantum numbers using these formulas. Okay, say for example if you have 3s, say yeah 3s. Okay, for 3s n value will be 3. Okay, this first thing is given by your principal quantum number, and s means l value is 0. Okay, so from this one you just find out radial nodes will be n minus l minus of 1 will be equal to 3 minus 0 minus 1 will be 2. Okay, and for angular nodes l will be 0, so for angular nodes l is 0, means 0 angular nodes will be there. Total number of nodes will be n minus of 1, so n minus of 1 is 3 minus of 1 is 2, means we have 2 radial nodes, and total number of peaks will be n minus of l, so peaks will be n minus of l, that is equals to 3. Okay, so in this one we can find, means for this one, for 3s, you see it is like this. Where is the radial distribution function? Yeah, this one is for 3s. Now you see we have 1 peak, 2 peak, 3 peak, so number of peaks is n minus of l, so 3 minus of l is 0, sorry 3 minus of l is 3, so this is the number of peaks we can find. Okay, so I think with this I'll conclude today's lecture. So if you have any doubts regarding this thing, you just post it. We'll have a doubt session. Okay, say yeah in day 3, in day 3 or day 4 we'll have a doubt session. So all of you just go through this video and try to take a book also along with you, and just compare the things and study a little bit. You'll understand it's very easy, not that tough. Just go to the basic parts. Okay, and if any doubt you just post it, I will just clarify it. Okay, so thank you, and yeah, let's do it. Chalo, bye.